Welcome to the course of Digital Signal Processing. Today we will continue chapter number 4, lecture number 6, sampling of continuous time signals. So in previous lecture I told you about the sampling of continuous time signals in time domain and their equivalent representation in frequency domain. Today we will look into the examples of sampling continuous time signals. So let's get started. So the contents of today's lecture are sampling and reconstruction of a sinusoidal signal. In this lecture, we will analyze with the help of examples the effect of changing the sampling frequency on the sampling and reconstruction of sinusoidal signals. So in this example, we will see the sampling of signal xc of t cos 4000 pi t and its reconstruction. So first of all, we have to sample this signal, and the sampling time is given to us, that is 1 by 6000. So we have to sample the first signal, that is xc of t, and we have to obtain x of n. Then we need to reconstruct the sinusoidal signal using the sampled impulses, that is xs of t, to get xr of t. So let's see how we can solve this. So as per the relationship between xc of t and xn, x of n, that is relationship between time domain signal and discrete time signal, we know that we can obtain a discrete time signal x of n if we replace small t with nt. So here we have the value of t, so xc of nt is just replacing t with nt, so the equation is same, it is cos 4000 pi nt. Now substituting the value of t, we will get cos 4000 pi n divided by 6000. Simplifying it, and you will get cos 2 pi n divided by 3. So this is the discrete equivalent of xc of t, and this is obtained by sampling it at 1 by 6000 samples per second. Okay, so comparing with the general form of cos, so this is the general form of our discrete time signal, that is cos omega naught n. So here omega naught is 2 pi by 3. Okay, so the continuous signal is cos 4000 pi t, whereas the discrete equivalent is 2 pi by 3n. Okay, and here the fundamental frequency is 2 pi by 3, whereas in continuous time the fundamental frequency is 4000 pi. So let's move on to next slide. So the first thing that you need to do when sampling is to check for aliasing. We know that how we can check for aliasing, using the condition omega s should be greater than twice the omega naught. Omega naught is the Nyquist frequency or the maximum frequency of the signal. In this signal, the maximum frequency of continuous time signal is 4000 pi. So we need to have omega s, that is sampling frequency, should be greater than 8000 pi. So here we are provided with time, so we can use the relationship sampling frequency is equal to 2 pi by t, that is angular frequency is equal to 2 pi by t, which is radian per second. So 2 pi divided by 1 by 6000 gives us 12,000 pi. So if you compare 12,000 pi is greater than 2 times the 4000 pi, so the Nyquist condition is satisfied, so there will be no aliasing and we will have accurate recovery and there will be no mixing of the copies. Okay, so in order to do this sampling process, we need to obtain the spectrum of xc of t. We know that xc of t is a sinusoidal signal, so we can represent the Fourier transform of xc of t like xc j omega is equal to, first represent cos in Euler form, then apply the Fourier transform, and everybody knows the Fourier transform of xc of t is pi delta of omega minus omega naught plus pi delta of omega plus omega naught. So there are two Fourier series coefficient, and one is on the left side, one is on the right side. and we know that the value of omega naught here is 4000 pi. So in last equation you can see that we have substituted the value of omega naught. So once one impulse will appear at 4000 pi with an area of pi, and the other impulse will appear at minus 4000 pi with an area of pi. So let's have a look at the spectrum of cos signal in next slide. Okay, so before looking at the spectrum of xc of t, what we are doing, we are finding the Fourier transform of sampled impulses. So we know that the Fourier transform of sampled impulses is basically the convolution of continuous time signal spectrum, that is xc j omega, with periodic impulse train. So we know that the Fourier transform of periodic impulse train is 2 pi by t summation k is equal to minus infinity to infinity delta of omega minus k omega s. So what happens when we convolve xc of j omega, that is the spectrum of continuous signal with many periodic impulses? So that spectrum appears on each sample impulse. Okay, so the overall amplitude become, the scaling become 1 by t. Why? Because 1 by 2 pi is because of the formula, and 2 pi by t is the area under the curve of impulse, and the amplitude of xc j omega is, if it is 1, so 1 by 2 pi into 2 pi by t, it becomes 1 by t summation, and then these are the copies xc j omega minus k omega. So the copy of xc j omega is appearing at multiple of sampling frequency. If k is 0, first copy will appear as the way it is in the original signal. Then the next copy will appear at sampling frequency when k is 1. The other will appear at 2 omegas when k is 2. So for this particular frequency, that is 1200 and 12,000 pi, that is sampling frequency, just substituting 12,000 pi in the above equation, so we can see that the copies of original spectrum will appear at multiple of 12,000 pi. So we have obtained spectrum of the continuous time signal, we have obtained the spectrum of sampled impulses, that is xs of t or xs j omega. So let's move on to next slide. So this will happen when you sample the continuous time signal with 1 by 6000. So you can see that our original spectrum was at minus 4000 pi, this one and this one. So this copy appeared at 0, and the amplitude and the area under the curve of impulse was pi, but because of the convolution it becomes pi by t. Now next copy will appear at 12,000 pi because of the sampling frequency. So we know that 12,000 plus 400, this will be 16,000, and 12,000 minus 400 will be 8,000. Likewise on minus omega s, minus 12,000 pi plus 4,000 minus 8,000 pi minus 12,000 pi minus 4,000 minus 16. So this is the spectrum, and now we are reconstructing it. How we can reconstruct it? I told you that we need a filter. There is the frequency response of low pass filter. We also call it reconstruction filter frequency response. So first of all, the gain of this filter will be t, and the cutoff frequency, this is the cutoff frequency, will be half of the sampling frequency. So sampling frequency is 12,000 pi, so it will be 6,000 pi and minus 6,000 pi. So if we apply the filter, we are left with this impulse and this impulse, which is the original xc j omega, because t gets cancelled with t. So we have accurate recovery. Now this slide is very important to understand. Previously we have sampled this signal, but the sampled impulses one is continuous domain. So we have obtained this signal xs j omega. This is not the Fourier transform of x of n. The Fourier transform of x of n is x e raised to j omega. So what we have to do, we have to replace that capital omega with small omega. So we know that small omega is equal to capital omega into t, or we can say that capital omega is equal to omega by t. So there is just the time scaling. We can see that the relationship between small omega, that is discrete angular frequencies, and continuous angular frequency is just this time scaling. So what we have to do, you see here, this is the exactly same Fourier transform which we have obtained in previous slide. Here the axis was capital omega. So what we did, we multiply it with time. Okay, so when you multiply it with time, you will have these values. Okay, so this is the copy at 0, this is copy at 2 pi, this is copy at minus 2 pi, next copy will be at 4 pi, 6 pi, 8 pi, and this is the maximum frequency, that is the cutoff frequency. Okay, now what happens, you can see here's the relationship x s of j omega, we replace it with x s j omega by t, and this is equal to x e raised power j omega. So once we do that, we have the property of impulse that whenever the impulse is scaled by t or any number, what happens is area under the curve changes to t delta of omega. So previously we have amplitude pi by t, but whenever you scale this impulse, it will multiply with t. So that's why you can see here we have area under the curve of pi. So impulses also scale. Okay, I hope you got it. So the only thing that you need to do in order to get the discrete time Fourier transform, you need to multiply the axis with t, and you need to scale the impulses. It means if this impulse is pi by t and you scale it with t, it will become pi. Okay, so previously the impulse was pi by t, so you have to scale it with t, because if we have impulse and this impulse is at omega and we just want to like expand it, we want to expand it. Expanding means if we do something like this, omega by t, this is expanding. Okay, so if we expand it, we cannot increase the width. What we have to do, we have to increase the area. So ultimately this is equal to t delta of omega. It means if the area was 1, now it will become t. Okay, so let's move on to next slide. So there is the final Fourier transform of x of n. So we have the signal xc of t, we sample it with sampling time this, we find out x of n Fourier transform, which is this. Okay, so x of n is equal to cos 2 pi by 3n. So this is discrete equivalent, this is continuous, and this is the Fourier transform of x of n. And here we are just seeing the reconstruction process again. So we have to find recovered signal xr of t. So how we can find it out? I told you that sampled impulses multiply with filter. So we apply filter on the sampled impulses. So this is the same continuous Fourier transform, and the impulses area is pi by t. This is our first copy, this is our filter cutoff frequency, this is filter gain. So if we apply filter, this is the filter on this signal, we will get the recovered signal, which is xr j omega. So we can see that if we apply this filter, only this impulse will come and this impulse will come, which is delta of omega minus 4000 pi, this one, and then plus delta of pi plus 4000 pi, which is this one, and the area under the curve of each impulse will be pi because the filter is t. So pi by t into t will be pi. So this is the Fourier transform. If I go back to if I take the inverse Fourier of this, it will become cos 4000 pi. So this is the exactly same signal, the recovered signal is exactly the same which we were sampling. Okay, So in this slide we will repeat the whole process. The only difference here is that we have changed the frequency of the signal. Previously it was 4000 pi, now we have changed it to 16,000 pi. So we will see that the effect of aliasing will appear in the reconstruction of undersample sinusoidal. This is undersample because we are sampling it with sampling time of 1 by 6000. So we have to sample the above signal and we have to reconstruct the continuous time signal from the sampled signal. So let's look at the steps. First of all, look why this time period causing the aliasing. So if I substitute, we know the relationship between discrete time and continuous time, so you just have to replace t with nt. So this will become cos 16,000 pi nt, and we know the value of t is 1 by 6000. So if you simplify it will become cos 8 pi n divided by 3. So now this signal is cos 8 pi n divided by 3. If you solve this cos 8 pi n divided by 3 and you solve this, both are same. It's just the integer multiple of this signal. So 2 pi into 4 becomes this signal. So there is no difference between this signal and this signal. Both will be drawn exactly the same way. So here if I see this, the fundamental frequency is 8 pi by 3. Okay, 8 pi by 3. So let's move on to next slide. So in this slide we are comparing for aliasing, whether we have aliasing, whether the Nyquist criteria is satisfied. So this is the Nyquist criteria. We have omega naught is equal to 16,000 pi, and we know that the relationship of omega s is equal to 2 pi by t. So we have t, so we will substitute t here, so it will become 12,000 pi. However, the value of omega naught, this capital omega naught, is 16,000 pi. So 12,000 pi, according to this condition, if we see 12,000 pi is not greater than 16,000 pi. So aliasing will appear, Nyquist criteria is not satisfied, copies will mix up. So we'll look into it. So this is the Fourier transform of xc of t. This is xc j omega. First impulse at minus omega naught, and then the second impulse at minus omega naught. So just substituting the value of omega naught, which is 16,000 and 16,000, and the amplitude of, or the area under the curve of each impulse is pi and pi. So this is the spectrum of continuous time signal. This is exactly the same spectrum as in the previous, only the frequencies are changed here. And again we know that sampled impulses are obtained by convolving xc j omega with periodic impulse train. So when we convolve periodic impulse train with xc j omega, what happens? We get the copies of xc j omega at multiple of sampling frequency, and these impulses are scaled by 1 by t. So substituting the value of omega s here, we get 1 by t summation k is equal to minus infinity to infinity copies of xc j omega at multiple of 12,000 pi. So here the sampling frequency is 12,000 pi, as it was in the case of previous example. The only thing is that here the frequency of signal is 16,000 pi. As I've told you in previous slide that if you want to obtain the Fourier transform of x of n, you have to convert sampled impulses Fourier transform into x e raised power j omega, and this can be done by scaling capital omega with t. Okay, so if you multiply the x's of capital omega with t, you will get small omega, which is discrete time Fourier transform. And because we are doing this, we are replacing omega with this. So you have to utilize this theorem that if you scale a impulse, like you are increasing its width, we cannot increase the width of the impulse. So ultimately what happens, its amplitude will get high, its area under the curve will increase. So let's move on to next slide. So we have also seen that this is the omega naught and this is the sampling time, and if we select this sampling time, undersampling will occur and aliasing will occur, and x of n is equal to cos 2 pi by 3n, cos 8 pi by 3n, both are equivalent. So that's why we are using the same terminology, cos 2 pi by n. It is equal to this cos 8 pi by n. This is just the fourth harmonic. So we have obtained the same sequence of samples. X of n is equal to cos 2 pi n divided by 3 by sampling two different discrete continuous time signals. So in one signal we have the frequency of 4000 pi, in other signal we have the frequency of 8000 pi, sorry 16,000 pi. So if we sample them with same sampling frequency, we obtain the same discrete time signal. In one case the sampling frequency satisfies the criteria, in the other case the sampling frequency did not satisfy the criteria. In example 4.2, the reconstructed signal would have frequency 4000 pi, which is not frequency of the original signal xc of t. So that's why we haven't drawn it, we haven't made the spectrum, but it is clear that because we are using the sampling frequency of 12,000 pi, so what happens, our copies will mix up and we will recover, the recovery will be of this signal. So this will be the same signal as we were having in the previous example. So that's why x recover is not equal to x continuous of t. I can just draw an example here, like these are the sampled impulses, okay, with area 2 pi by t. This is 0, this is 12,000 pi, and this is minus 12,000 pi, and then this is our signal, two impulses, pi, this one is at 16,000, this one is at 16,000, positive, negative. So the first copy will appear at 16,000, the first copy will appear at 16,000 pi. Now the second copy will appear at 16,000 minus 12,000, which is 4,000. So this is the first copy will appear at 4,000 pi. Now the upper copy will appear at 12,000 plus 16,000, that will be at 28,000 pi. Likewise for this minus 12,000 plus 16,000, this will appear at minus 4,000 pi, okay, and then the other will be at minus 28,000 pi. So if we recover, we are going to recover this two copies, that is 4,000 pi and minus 4,000 pi. So that's why our recovered signal is cos 4,000 pi t, which is not equal to cos 16,000 pi t. So the point here to make is that if we have the same sampling frequency but original signal is changed, we will obtain the same sequence of samples, okay, we will obtain same sample of sequence. Here is another example of aliasing. Our original signal frequency is cos 4000 pi t. So the frequency here is capital omega naught is 4000 pi. The sampling time is reduced to 1 by 1500, and we will sample this signal to obtain x of n, and from this x of n or sampled impulses we will recover the original signal. So let's move on to next slide. So here's our continuous time signal. This is our sampling time, and this is the relationship between discrete and continuous signal. So how we can sample it? We have to replace capital T with small nt, which is the multiple of sampling time. So if we replace it, we will get cos 4000 pi nt. Now capital T is 1 by 1500, so replace it. We will get cos 8 pi n, which is the same sinusoidal signal as we have in the previous case. So it means that if I sample the signal at different frequency, I get the same discrete time signal. Okay, so comparing with the journal form, if I compare it with this, so our omega naught is 8 pi by 3. So we are getting the same discrete time signal even if we are sampling a different time period. So let's move on to next slide. So in this slide, our omega s is 2 pi by t. So t is 1 by 1500. So 1500 multiplied by 2 pi, it will become 3000 pi. Whereas omega naught is 4000 pi. So clearly 3000 pi is not greater than 4000 pi. So the condition is not satisfied, and we will not be able to recover this xc of t. Okay, so aliasing will appear. So this is the spectrum of the continuous time signal. We have the same continuous time signal as we have in previous case. So xc j omega is equal to pi delta of omega minus omega naught plus delta of omega plus omega naught. We know that there are only two components of cos. So xc j omega is equal to pi delta of omega minus omega naught. So omega naught here is 4000 pi, so we are substituting the value of 4000 and minus 4000 pi in this spectrum. So we will have two impulses. The spectrum will be like this: 4000 pi and minus 4000 pi, and this will be pi and this will be pi. So this is the spectrum of this xc j omega. So let's move on to next slide and see what expression we get for sampled impulses. So we know that the expression of sampled impulses, that is the Fourier transform of x s of t, is 1 by t scaling summation, and then the copies of original spectrum, the copies of cos spectrum at multiple of sampling frequency. So the sampling frequency here is 3000 pi, so substituting here we will have sampled impulses at multiple of 3000 pi. So let's move on to next slide. So our original spectrum was this: 4000 pi, this pi, pi, 4000 pi, this was xc j omega. Then we have periodic impulse train. I'm just going to draw 3. The area under the curve of these impulses was 2 pi by t. This was 0, this was 3000 pi, and this was minus 3000 pi. So this was s of j omega. So if I convolve this, we know that s of j omega is equal to s of j omega convolved to xc of j omega. So after convolving, we will get this signal. So how we get this signal? First of all, 0 with this, so our spectrum will become 4000 pi, 4000 pi. So now next we have to move the 0 to 3000. So the center point, this will appear at, the first copy will appear at 3000, minus 4000, so it will appear at minus 1000. Okay, so it will appear at minus 1000. Let's say minus 1000 is this point. Okay, so you can see here. So the above copy will appear at 3000 plus 4000, so it will be at 7000. Okay, so this is it. You can see here it is not visible here clearly, so it will appear at 7000. Now if I go back to minus 3000, minus 3000 and minus 4000, one copy will appear at minus 7000, and the other copy minus 3000 into plus 4000, it will appear at 1000. So here we have 1000 pi, here we have minus 1000 pi, and the other copies are appearing at, you can see the next copy will appear at 2000 and 4000. So at 3000, if we have center point at 3000, this is actually not right. So this is wrong. Just forget about this thing, just forget about this. These are not right points, just forget about this. So minus 1000 and 1000, and the cutoff frequency of the filter will be half of the sampling. So sampling frequency is 3000 pi, so the half will be 1500 pi. So if we apply filter here in this region, the gain of the filter is t. So what we are going to recover, we are going to recover cos 1000 pi t, because these impulses are at 1000, which is not equal to cos 4000 pi t. So this is the discrete equivalent just obtained by multiplying time. There is 1 by 1500 in the previous slide, as you have seen. So we have obtained x e raised power j omega. You can obtain this x e raised power j omega by multiplying the angular capital omega with t. So we obtain this small omega, and the next thing that you need to do is to scale these impulses. So these impulses will scale with t. So previously it was pi by t naught, it will become pi. So this is the Fourier transform of x of n, which is x e raised power j omega evaluated at omega is equal to capital omega. So we have found out the x of n, the Fourier transform of x of n. We have seen that x of n is equal to cos 8 by n, which is equal to cos 2 pi by 3n. So the takeaway from this example is that the same discrete time signal may result from sampling the same continuous time signal at two different sampling rates. So here we have the same discrete time signal we are obtaining. We are obtaining cos 2 pi by 3. Okay, so obtaining the same discrete time signal by sampling the continuous time signal at two different rates. And in previous slide we have seen that we get the same discrete time signal by sampling a different sampling rate. Okay, or if the two continuous time signal are different and we sample and at same sampling rate, we again get the same discrete time signal. The reconstructed continuous time signal would have frequency this omega naught 1000 pi naught 4000 pi. So recovered signal will be this, which is not equal to the continuous. So one takeaway is that if discrete time we get the same discrete time signal if we are sampling at different sampling time. Number two, we get the same discrete time signal if we have the same sampling time but we have different continuous time signal. So takeaway, it is possible to get same discrete time signal in the following two scenarios: when two different continuous time signal are sampled using the same sampling rate, as we have seen in first and second example, and then we have seen that same continuous time signal is sampled using two different sampling rate. So this is example number 3. Aliasing occurs when Nyquist condition is not satisfied. Okay, so this is the takeaway, that we get same discrete time signal when we are sampling a different sampling rate, or when we are sampling a same continuous time signal with two different sampling rates. Okay, so let's move on to next slide. So read the book section 4.0 to 4.2 of the Oppenheim book, that is your course book, and then practice out this problem for 4.1 to 4.4 and 4.8 to 4.11. Some of these problems are in your assignment as well. Thank you very much.